Today you will see our EVM interpreter precompile used as a trustworthy compute engine. We have here a spreadsheet powered with Web3 functionality, and you can call smart contracts and execute transactions on the Ethereum network. And I have demoed such Web3 spreadsheets in the past. Links are in the description. But today, I will show you something that nobody else has thought about: composing and executing bytecode using an EVM interpreter precompile that gives access to context data, like what remains on the stack when an operation has ended, or how many reads and writes and calls has a bytecode fragment executed. So let's start with something simple. We can write EVM assembly, so let's add some numbers. Let's push 3 on the stack, then 4, and then we can add them. The result is both in our Taylor EVM language and in bytecode. And now let's try returning the result. We store the result at this key, and the value is the add result. And then let's return it. We push a value of 32, which is the size of the return value. And then we return the value in memory at this key with this size. And then use list to combine this code and this code. So we have this bytecode at position H3. And now we can use the interpret function. Which receives the bytecode, the call data, which is empty right now, the gas limit, and the value in way. And we get the result, 7, which is ABI encoded, and it's 3 plus 4. But there is more. We can provide the bytecode, input, and current stack to the analyze fragment function instead of interpret, and we will get the result, the output stack, and some execution information that I will show you next. So this means that we can compose fragments of code individually right in the spreadsheet, and the analysis of such fragments is done on-chain in a controlled environment that is trustless, or better said, trustworthy. So this time let's change from adding 3 and 4 to just adding 3. Because the other argument will be taken from the stack that we will give as input. Next, we push 1 and use this 1 as a storage key. So we store the value of this addition at key 1. And this is done by the store command. We store at this key this value. And now let's sload the value at from the same key. So we can use the same spreadsheet cell as we used for the store key. And let's use list to concatenate the code. So this is the bytecode fragment that we will use. And notice that this fragment doesn't have a return opcode. And this will be our input stack. So this is the value that will be added by this instruction. And the analyze fragment function receives this fragment bytecode along with this stack, which we will parse as JSON, a gas limit and the weigh value. And we get these results, which are the number of read operations from storage that the fragment has executed, and we have one sload, the number of write operation, and we have an store, the number of calls to other contracts, and we have 0, and the total memory size that was used to compute this. And if you see the fragment doesn't work with memory, it only works with stack and storage. So this is 0. And this is the amount of gas that was left over from the gas limit that we gave. And this is the stack at the time of output. It contains this value, which was put on the stack by the sload operation. And it is the result of adding our input from the input stack in this add operation. So let's change the stack to have a value of 2 here. And now we have 5, which is 2 plus 3. So this spreadsheet becomes the most detailed EVM IDE, with direct access to the execution context and statistics about the most important EVM operations. In this demo, you have seen an on-chain, consensus-based and verifiable engine that can be used for spreadsheets. It uses the chain's global environment and the EVM itself, and it is trustworthy. There is no need to rely on a centralized entity to provide correct computing. And you can use it on any mainnet network to actually test your bytecode in the global environment of that mainnet without putting any funds at risk. Ease of use, because spreadsheets are familiar to the financial sector. And this is the most flexible dApp, a generalized dApp where an entire application can be replaced with a macro or a plugin. It has support for Taylor compiled. So this is also an IDE for developing smart contracts. In future videos, we will talk more about how this tool fits into our vision of true decentralization.